Hello everyone, my name is Rowan Barashon. Today I'm going to be talking to you a little bit about the Alekseevskii conjecture in 9 and 10 dimensions. In particular, I'll be discussing some of the work that we did last year in order to try and verify the conjecture in 9 and 10 dimensions, and we'll give you a bit of an idea of sort of where we went with that problem. I'd like to thank the MCA and the organizers of this block for giving me the opportunity to give this presentation today. Before we begin, I'd like to discuss a little bit about where we're going to be going with this talk today. First, we'll begin by discussing sort of the motivation of the problem and where it sits in the field of Riemannian geometry. After that, we'll move on to the strategy that we chose to adopt and how we used it in order to resolve this problem. That will involve, first of all, a classification step, and then later on, analyzing the examples that we found in the conjecture. And then finally, I'll give you a bit of an idea of sort of where we've gone with this problem at this point. The Alekseevskii conjecture arises quite naturally from studying the following problem. Given a smooth manifold M, what is the metric G best adapted to the geometry of this smooth manifold M? Of course, this problem is quite difficult to resolve in general, so what we do is we make certain assumptions. We can, for example, choose to take certain constant curvature assumptions. If one, for example, chooses to say, well, what happens if we have a constant sectional curvature Riemannian manifold, then what one recovers is the problem of finding the simply connected spaceforms. And what you find is, well, if you've got a constant sectional curvature complete Riemannian manifold, then this has to be locally isometric to one of the three spaceforms. Either your manifold has hyperbolic, Euclidean, or spherical geometry, when your curvature is negative, 0, or positive, respectively. And we can generalize further beyond this as well. We can say, well, maybe our guess for constant scalar curvature was too restrictive, and instead maybe it might be better to impose different curvature assumptions, for example, constant Ricci curvature. Maybe as well we can choose certain topological assumptions on our Riemannian manifold. Say we assume that our manifold is compact. Maybe we can assume that it's simply connected instead. And we can impose other assumptions as well, for example, special holonomy assumptions. Now, in our case, we're going to be largely interested in studying those manifolds which have constant Ricci curvature. And recall, a manifold is called Einstein if its Ricci curvature is a scalar multiple of the identity. And well, now the goal here really is to understand the geometry and the topology of these manifolds. The issue, of course, is that the Einstein equation, given by equation 1 in the slide here, is a second-order nonlinear partial differential equation. Worse still, there are no general existence results for the Einstein equation for arbitrary Riemannian manifold. And the question now is, well, how do we get around this? In our case, we choose to impose certain symmetry assumptions. And the way to do this is to impose certain conditions on the isometry group of our Riemannian manifold. In our case, we're going to be assuming that our Riemannian manifold is homogeneous. One can also go on and study, for example, cohomogeneity 1 manifolds. Recall now that a manifold is called homogeneous if it is given by the quotient of a Lie group G by some closed subgroup of G given by H, where G acts transitively on our smooth manifold. If we equip our homogeneous space with a homogeneous Einstein metric, that is a Riemannian metric for which G acts on the Riemannian manifold by isometries, then what we find is actually that the problem from before, whether or not we have existence of Einstein metrics, largely depends on the sign of the Einstein constant. Now, if the Einstein constant has positive sign, then we find that by the Bonnet-Myers theorem, our Riemannian manifold has to be compact. On the other hand, if our Riemannian manifold has zero curvature, i.e. our manifold is Ricci flat, then what this implies is, well, our manifold has to also be flat. Now, this is a result that was proven by Alekseevskii and Kimmelfeld in 1975. Finally, we have, in the case of a negative Ricci curvature, all that we've really been able to find so far is that our Riemannian manifold needs to be non-compact, and this was due to Bochner in 1948. Already in the first two cases, we attained quite a lot of information. In the first case, we attained that our manifold is compact and that it has finite fundamental group. In the second case, we find that our manifold is actually just the product of Euclidean space and a flat torus. But in the last case, we don't have quite the same sort of result. All we have is that our manifold is non-compact. And so in the case where we have a homogeneous manifold, which is non-compact, we still have the following major unresolved problem. which states every connected homogeneous Einstein manifold with negative Ricci curvature is diffeomorphic to Euclidean space. So actually, this conjecture provides very strong topological conditions on our homogeneous Riemannian manifold, namely it has to be simply connected. And so, well, at least from the topological point of view, this motivates sort of why one might be interested in studying this conjecture. From the geometric point of view, one is interested, of course, in trying to classify these Riemannian manifolds explicitly. So far, we've seen some major steps in already trying to understand the structure of homogeneous Einstein manifolds, mainly in lower dimensions, but also some cases in general as well. For example, if our homogeneous manifold is symmetric, then actually it has to also be diffeomorphic to Euclidean space, since it's given as a solved manifold. In dimensions at most 8, it's already known that this conjecture holds in almost all cases, except for a few Lie group examples. And in dimensions 9 and 10, if G is non-unimodular, that is non-semi-simple, a result due to Arroyo and Lafuente in 2016 shows that again this conjecture is resolved in this case as well. And so finally what we're left with is studying the semi-simple, i.e. unimodular examples of homogeneous spaces. And in this case, a result due to Jablonski and Peterson in 2017 shows that in fact G also has no compact simple factors. So what one can do is they can assume that G is unimodular and proceed with trying to prove the conjecture only on the cases where the transitive group is semi-simple with no compact simple factors and where the homogeneous space has dimension 9 or 10. To recap, in order to verify the Alekseevskii conjecture in 9 and 10 dimensions, it suffices for one to consider the homogeneous spaces of the non-compact type for which the Lie group G acting transitively on this homogeneous space is semi-simple and has no compact semi-simple factors. And now in this case, what we can do is we can actually break this investigation into two distinct steps. The first of these is to understand non-compact 9 and 10 dimensional homogeneous spaces which aren't diffeomorphic to Euclidean spaces. In this case, again, we can assume that our Lie group G is semi-simple and doesn't have compact simple factors. Moreover, we can assume our homogeneous space is non-symmetric, since if it were symmetric, it would be diffeomorphic to a solved manifold. And then after completing this step, what one can do is they can analyze each of these cases and show non-existence of solutions to the Einstein equation for negative Einstein constant in each of these cases. And now in order to do this, one needs to first of all understand the space of invariant metrics on these homogeneous spaces, and this can be quite complicated, and then use certain formulae for the Ricci curvature to try and simplify these computations. In the first part, our job is to provide a list of all non-compact homogeneous spaces whose Lie group is given as a product of simple factors. We can assume, of course, that each of these simple factors are non-compact and that our manifold itself is non-symmetric. Now, the main geometric tool that actually aided us in our classification was the observation that if we have a homogeneous Einstein manifold with negative Einstein constant, then none of these simple factors can have an ideal isomorphic to SL2R. And so the problem now reduces down to finding all non-compact homogeneous spaces with semi-simple transitive group with no simple factor isomorphic to SL2R. And this actually helps to remove almost half of the potential cases that we could have had to investigate in this classification, since what one can do is they can take for any homogeneous space of dimension 6 or 7, you can then construct a new homogeneous space given by the product of SL2R in this original 6 or 7 dimensional homogeneous manifold, which provides a new case that one would have to investigate. And so, as I said, you can remove quite a large variety of these cases just from using this theorem alone. And so it really is this result here that reduces the classification and makes this problem far more tractable for our methods. This classification problem 2 essentially boils down to finding the subalgebras of non-compact semi-simple Lie algebras. It turns out that this problem is actually quite difficult to resolve naively, and so what one has to do is they have to sort of try and sidestep the problem. If instead of considering the non-compact semi-simple Lie algebras, one instead chooses to try and find the subalgebras of compact semi-simple Lie algebras, then what one finds is that this problem is actually already solved, and lists already exist for low-dimensional examples. Fortunately for us, a result due to Nikonov in 2000 actually provides a partial duality between these two problems. The construction of this partial duality in particular comes out of studying the duality between irreducible symmetric spaces of the compact and non-compact types respectively. In order to carry out this classification, what one first does is start with a compact semi-simple homogeneous space. That is a homogeneous space whose Lie group is compact and semi-simple, and we write for each of these compact simple factors of our homogeneous space the projected isotropy, which we will denote by Hi, for each of these compact simple factors. What one now assumes is that in each of these simple decompositions, these GIs modulo HIs, there exists a maximal subalgebra sandwiched in between this HI and this GI, such that the quotient GI modulo KI is an irreducible symmetric space of the compact type. Now that we have an irreducible symmetric space of the non-compact type, what we can do is we can dualize to an irreducible symmetric space of the non-compact type, and in this dualization identify an isomorphic subalgebra to this HI term, obtain a homogeneous space GI modulo HI for which G is non-compact and H is a subalgebra of K. Now already we can see here that we've got some choice. What we find is that actually this is a partial duality. We don't attain exactly one homogeneous space for every compact homogeneous space. And so by taking all possible maximal subalgebras which give rise to irreducible symmetric spaces of the compact type, this gives all possible non-compact homogeneous spaces with semi-simple transitive group and no compact simple factors. For example, if we consider the homogeneous space or the compact homogeneous space SO5 modulo SO3, SO3 has two maximal subalgebras in SO5, that is SO4 and SO3 cross SO2. And now in both of these cases, each of these are symmetric spaces of the compact type. And so they can be dualized to non-compact symmetric spaces of the non-compact type. Then, taking the subalgebra isomorphic to the subalgebra given in the original homogeneous space, we attain a non-compact symmetric space with only simple factors, none of which are compact. And so what we find is there are actually two non-compact duals of SO5 modulo SO3. These are actually given by SO41 modulo SO3 and SO32 modulo SO3. And so the problem now is to find for each compact homogeneous space with semi-simple transitive group all of their corresponding non-compact duals and write them all out in a list. And so this is the first step of our classification. So we found for each compact homogeneous space in dimension 9 and 10, their corresponding symmetric spaces, and their corresponding non-compact homogeneous duals. The goal here, of course, now is to show non-existence of Einstein metrics in all of the examples that were detailed out on the list. In general, of course, the Einstein equation is a nonlinear second-order partial differential equation, and so finding non-existence of Einstein metrics can be quite a difficult problem. If we now decompose our Lie algebra G in terms of its reductive decomposition, H plus M, and decompose M as Q plus P, where our factor Q lies entirely within the maximal compact subalgebra K, then what we find is actually the space of G invariant metrics on our homogeneous space is equivalent to the space of commuting endomorphisms on this Q plus P factor of our homogeneous space. Then, using formulae for the Ricci curvature and this identification of G invariant metrics with intertwining endomorphisms for the adjoint representation, one finds that this partial differential equation of the Einstein equation actually reduces down to an algebraic equation. And so we can use computer tools, if necessary, to try and simplify our formulae further. What one also finds is that a result due to Nikanorov proves that if any of these pi irreducible factors are isomorphic to any of the qj irreducible factors in the Q representation, then in fact this homogeneous space admits no Einstein metrics, invariant Einstein metrics with negative Einstein constant. What we're left with is very few cases to check, and we can check each of these cases directly. In order to provide an example of how one might go about trying to prove the non-existence of Einstein metrics for one of these remaining cases, let's consider the case of SLN plus 1R modulo SOM. This, of course, has maximal compact subgroup SON plus 1. Its isotropy representation decomposes into its irreducible submodules in the following way, where we can write H as being the upper block of the matrix, and then the isotropy representation decomposes in the following way. Observe, moreover, that in fact P1 and Q1 are isomorphic as representations to each other. And so this is well and truly one of the cases that Nikanorov's result can't factor out. Now in the case where n is equal to 2, the dimension of our homogeneous space is 7, so this isn't actually one of the examples that we are interested in specifically, but the computations do simplify greatly. What one finds is that the space of SL3R invariant metrics can be parameterized by real symmetric positive definite matrices of the following block form, with A, B, C, and D all positive, and E squared less than BC. In a particular orthonormal basis, one of the off-diagonal terms of the Ricci curvature actually takes the following form. And now, in order to prove non-existence of Einstein metrics, one can proceed by contradiction and assume that one does have an Einstein metric, and then try and provide conditions on the parameters A, B, C, D, and E. Now, in order to have an Einstein metric, what one would expect is that this Ricci curvature should be 0. And what one can do is they can try and find solutions for the Ricci curvature in the 2,4 component being 0, and to try and prove that such a result would provide a contradiction. And so now what one can do is they can use this as a jumping platform in order to try and do the exact same thing on the remaining cases. And now going out and doing this, what we've managed to do is find a strict bound on the sort of the number of potential exceptions that we could find to the Alekseevskii conjecture. We've managed to prove that if our homogeneous space is not given by SP11 on the diagonal component of U1, or any of the Lie group cases following, then actually M is diffeomorphic to Euclidean space. And now, what one recognizes first of all is, of course, the list of exceptions. This isn't a list of exceptions per se, but a list of potential exceptions, cases that we weren't able to resolve ourselves. And an important thing to note here is that apart from SP11 modulo its diagonal U1 factor, all possible exceptions are non-compact, real, semi-simple Lie groups with left invariant metrics. A natural question that might arise, of course, is, well, why did we stop at 10 dimensions? Why not continue on to 11 dimensions or 12 dimensions, and so forth? And so there are a number of reasons why our methods don't extend to 11 and 12 dimensions and so on. The first of these, of course, is that there are no results in the non-unimodular homogeneous case. And so our results rely on, first of all, considering just the unimodular case of homogeneous spaces. Moreover, in 11 dimensions, we have examples of spaces like SL2C cross R, semi-direct product with C2. And so the Einstein equation on this actually reduces to an equation for left invariant metrics on SL2C, which is an even more general equation than the one that we're trying to resolve in this Alekseevskii conjecture. Of course, there are also new examples of homogeneous spaces in 11 and 12 dimensions with small isotropy, and the big obstacle with trying to resolve the Alekseevskii conjecture is these small isotropy examples, because what one finds is that if you have a smaller isotropy, then this homogeneous space has a more wild and varying space of invariant metrics. And so I might leave it here. Thank you for coming to my presentation. I hope you enjoyed it.